Hello everyone and welcome to today's Streamline session. Today's Streamline is brought to you by AIRAH and Ecolibrium. This webinar will look at the NCC 2019 with specific regard to the changes to Section J building fabric TDS requirements covered under Part J1 of the NCC 2019 Section J. We'll also go through a couple of case studies today as well. Just a reminder, any questions, please type them into the Q&A and we'll go through them at the end of the presentation. So now I'd like to pass things over to our presenter for today, Grace Fu, who will be taking us through today's session. So Grace, I might pass things over to you.
Excellent. Thank you, Marie, and hello everyone. My name is Grace and I am from Delta Q. We're essentially a energy efficiency and sustainability consultancy, but the big part of the role that I played and the wider team played was in the 2016 to 2019 National Construction Code changes. We were the project team that did a lot of the technical analysis underlying this work. For today's presentation and a case study, I would like to also acknowledge my colleague Hong Sen, who did some of the modeling work in our second case study. Okay, so for today, we're going to go through three main topics. The first is we're going to go through an overview of the changes to the building fabric requirements, which is currently covered under Part J1. The changes for wall glazing requirements are quite substantial compared to 2016. So we will spend some time looking at what is required now. Then for the second half of this presentation, we'll go through the case studies. Some of these case studies will be published in Ecolibrium in the next publishing cycle. So it's either this month or next month. So if you miss any detail, you can look at the details there as well. But with the case studies, we have two parts to it as well. The first is just going through a standard office building with curtain wall construction and just trying to see how we have to change the design on the wall glazing construction in order to achieve compliance to Section J. In the second case study, we're not so much looking at compliance anymore, but we're just looking at the overall impact of changing or the performance of building fabric, such as your glazing performance on the building's energy consumption, peak loads, and thermal comfort, largely because we are AIRAH, so we are in the industry of providing building services for aircon. All right, so looking at the first part of our presentation now, what are the new building fabric requirements in Part J1? So if we look at the 2019 code, which you can log on and get for free off the ABCB, Australian Building Codes Board website, Part J1 covers everything related to the building fabric, which is the surrounding envelope that covers or encloses that building. So Part J 1.2 covers your general requirements. It generally covers your construction quality. With J 1.3, it covers roof and ceiling construction. J 1.4 covers roof lights, particularly more relevant in smaller buildings, not so much our large commercial buildings. J 1.5, which is the focus of our presentation today, covering wall glazing construction, and J 1.6, which covers full insulation requirements. Now, with the wall glazing construction in 2016, some of you will know that it used to be covered in Part J1 and J2, and we're looking at the wall performance and the glazing performance separately. In the 2019 code, there's a recognition that we should be looking at the building design and performance more holistically. So you see a lot of the trends throughout today's presentation when we start looking to say, well, holistically, how does the building perform? So let's look a little bit deeper into Part J 1.5. There are two parts to it. The first part is looking at the system U value, and the second part of it is looking at this solar admittance. All right. So with this system U value, so U value basically stands for the thermal transmittance through the I guess construction in question, and it's actually just the inverse of the R value, which is how resistant is that construction to heat transfer. So with the DTS requirements, or deemed to satisfy requirements, limits have been set for the actual wall glazing construction. That is to say, depending on which climate zone your building is located in, there is a maximum U value that you can have. So the higher the U value, the higher the heat, the thermal transmittance, and therefore more heat loss or heat gain. Okay, so you want your U value to be as low as possible, and definitely lower than the limits set in the code. We also have separate limits for total system U values for display glazing, and that is basically to recognize that with display glazing, sometimes you can't achieve the U value required while still maintaining the same level of visible light transmittance. So letting people, the main function of display glazing is to let people look into, I guess, the shop front and see what is on display. And that's why there is dispensation for a poorer U value performance for display glazing, particularly related to class 6 type classes. Now, in addition to that, we also look specifically at the wall components. So when we talk about wall components, we're talking about opaque wall components. So that's where you can actually see through that construction. That could be in the form of cladding, it could be in the form of concrete or brickwork or masonry. Or it could be spandrel panels. So in the 2019 code, spandrel panels play a bigger role, and it's now specifically in its own section that gives you guidance on how you deal with it. So on the wall component, opaque wall component, there are different requirements for depending on whether your window to wall ratio is less than 80% or more than 80%. Essentially what that's saying is that, does your building have more wall than window, or does, if there is a lot more wall, so if there's at least 80% of your facade is wall, then the R value requirements, so the resistance to heat transfer requirements for that particular assembly is higher compared to if you had more glazing than opaque wall. So there are specific calculation methods referred to in specification J1.5a. So that tells you how, it gives you formulas on calculating total system U value. With the glazing component for U value, you need to make sure that it's not just talking about the glass itself. The system U value needs to also include heat loss, or the U value of the framing. Okay, so that's where we start considering things like thermally broken or non-thermally broken frames. Now, the second part of wall glazing construction requirements is solar emittance. The concept of solar emittance is basically a function of how much window you have or how much glass you have in your construction. So how much, what your solar heat gain coefficient of your glass is, and also whether you have external shading or not. Again, for this, we have limits set for the entire wall glazing construction and separate ones for display glazing. Once again, detailed calculation methods for the formulas are found in specification J1.5a. So for both system U value and solar emittance, there are two methods for assessment. When I give my initial presentations when 2019 National Construction Code was first rolled out, I described it as one, either using a recipe book method where you're following every single provision and recipe in there and say, for each aspect, I'm going to comply separately. The second method where we start to look at the multiple aspects of holistically looking at the whole building is a bit like you taking the same recipe and then taking ingredients in and out. So for example, you could be substituting, eggplant for zucchini, for example, and you might still end up with the same good tasting curry, and it's still high performance. So the same sort of concept with the wall glazing requirements for both system U value and solar emittance. In which case, if you can't, you can either try to comply on the north, east, west, south aspects separately, or if you find that one aspect doesn't comply, you can look at it as a whole that is area weighted to see if you comply. So back to our concept of U value. What are the key changes that we need to be aware of? One of the things that has become front and center is the concept of thermal bridging. Well, the 2016 code has always had the reference to the Australian standard, New Zealand standard 4859.2, which dictates the performance of the construction of a building and its thermal properties. It was never clearly stated, I guess, explicitly that thermal bridging needed to be calculated when you are referencing your external wall R value or U value. And what that meant was that a lot of practitioners went, okay, well, if I put 2.5 R value of 2.5 insulation between my walls, then my external wall performance is R2.5. And what we found that with thermal bridging, particularly from impacts like framing, where you can see here in this image that this frame actually, this stud, sorry, doesn't actually have insulation. So there's a bridge that allows heat flow to go through. Now, when that happens, it can actually undermine your insulation R value by more than 40%, just purely because of thermal bridging. And therefore, it's very important, particularly when you're doing your modeling, if you do modeling, to incorporate the impacts of thermal bridging in your energy model. Of course, with thermal bridging, there are other issues around it. If you have thermal bridging, it often causes localized cold spots, which can lead to condensation issues and mold problems, particularly interstitial condensation, which means that you get mold growing behind your walls, and that's really bad because if you can't see it, you often can't fix it until it's too late. So the New Zealand standard 4214 is a very important resource for all of you. It is free, and I recommend that you download that if you were a practitioner. The second part that is very different is spandrel panels now get their own section in the National Construction Code covered under specification J1.5b. There are two ways or two methods that specification J1.5b provides to you to deal with spandrel panels. The first is they give you 4 what we call beam configurations. So they tell you the configuration of whether you have a thermally broken or non-thermally broken frame, because your spandrel panels often sit within the frame. And then they'll also provide you with a few configurations telling you, I guess, what the air gap is between your spandrel panel and your back pan. So you often with a spandrel panel configuration, you'll have let's call it the glass or the spandrel, and then you get an air gap, and then you have a back pan that holds your insulation. So if you can somehow match your construction to those 4 configurations, then you can just use the deem values in there in your assessment. If you can't get that to match, then they've provided you with a formula, and that's a formula that you can see on the screen there. It's basically a function of so with a spandrel panel, or indeed in any glazing unit, the U value of your edges, the edge of your panel, in the center of your panel, and the U value through your frames, aluminium frames, for example, are all different. And so what this formula does, which is taken off from the NFRC 100 method, is it does an area weighting for you to tell you what your total U value of your spandrel panel performance is. And this is really important to note. With spandrel panels, they're notoriously known to be poor performing. So if you had a R2 insulation within your spandrel panel, even if your frame was thermally broken, so your aluminium framing, you still only end up with a net R value of only 1.09. So you can see that in specification J1.5b. So with spandrel panels is known to be really poor performing, and with the rise of curtain wall constructions in industry, it's really important that we model it correctly as well. Okay, so looking a little bit more deeper into thermal bridging, this is an example here that is not the curtain wall construction. This is a standard lightweight steel frame construction here with a metal cladded wall. So the ABCB has published a facade calculator for you, and this diagram is taken from Eric O'Kenna's presentation in the AIRAH Building Simulation Conference from 2017, but you can also see this in the New Zealand Standard 4214. The parameters that you need to know in order to use the facade calculator is, one, you need to know what the spacing between your cavity is, so that's 92 mils in this case. You need to know what your stud thickness is, and often that's quoted in terms of base metal thickness. And here it's a 1 mil thick flat metal framing stud. The other thing you need to know is the flange width. So that's the 47 mils that you can see here in this example. And finally, you also need to know what the distance between your studs, all right, and also your noggings in your construction. So that's when we're looking at it vertically now, from the top of the wall to the bottom of the wall. So all of these parameters are what you need to know in order to calculate or use the facade calculator or the New Zealand Standard 4214 formula to calculate the net thermal resistance, so the R value of your wall construction. Again, as a reminder, often your insulation will sit between your metal studs. If it's R value of 2, with thermal bridging, it often is not going to be an R value of 2. It's probably going to be a 1 point something R value. So with the system U value, what does the code require? So let's start from the left side. So on your wall glazing construction, so that's the total U value of your wall and your glazing combined. For all classes on the top there, classes 2, 5, 6, 7, 8, 9, except for the ward, your requirement is you can't exceed a U value of 2.0. And essentially, I like to classify that into sort of daytime buildings and then overnight buildings. So you can see that in overnight buildings, class 3, which is a hotel, class 3, 9 or 9A, your U values is 2.0 in climate zones 2 and 5. So that's sort of like Brisbane and your Sydney, Perth, Adelaide. But then once you get to a colder area, in the Alpine area in climate zones 8, your U value is 0.9. And it's U equals to 1.1 for all other climate zones. So more stringent compared to a daytime operation building. With display glazing, I've mentioned to you that you get a dispensation just because of the nature of what display glazing is. So your U value requirement is 5.8. Often you'll be able to get away with just a single glaze unit. I also talked to you earlier on about the requirement for opaque wall components. So yes, the code is a little bit confusing because it cycles between R value and U value, but just remember that a U value is the inverse of R value. So with R value, you're measuring the resistance of the construction to heat flow, and therefore the higher R value, the better it is. So when you have a lot of window compared to the wall, so that's window to wall ratio, then your R value requirement, that's a backstop, is 1.0. But if you have more wall than window, then your R value requirement naturally becomes higher. So it's 2.4 in climate zone 1 and then 1.14 everywhere else. And then again, for overnight buildings, it's a little bit more stringent, as you can see, ranging between 1.4 and 3.8 in a colder zone. With the solar admittance, if you're looking at it from a single aspect perspective, so that's where you're looking at only on the north, east, west, and south, this is the formula that denotes your calculation for solar admittance. Essentially, it's your window to wall ratio multiplied by your shading factor. So multiplied by your solar heat gain coefficient of your window. So that's your glass past the frame. So with the shading coefficient, there are tables in the code, part J1, that tells you for a given projection, so distance away, how far it projects away from your actual window, and then depending on the height of it, what the actual coefficients you would use is. Now, I mentioned before that this code is now becoming a little bit more flexible. So if you find that you can't comply on every single aspect, so on north, east, west, and south, all of them comply. If you can't do that, you can actually revert to something that's similar to the 2016 requirements, which is calculating the representative air conditioning energy value. So what is it? It's basically just an area weighted value for your solar emittance across each aspect. So A is the area of your particular aspect, so it could be your north, multiplied by the solar emittance that you had calculated previously. And then there is an alpha value. So there are slightly different weightings in the code, so it's in the table, that tells you what the coefficient is for the north, south, east, and west separately. All right. So for example, in Australia, we are in the southern hemisphere. So on the southern aspect, it's probably not as important compared to, say, the north, east, and west to control solar emittance. So what are the limits in the code? In the code, with your wall glazing construction, the allowance is between 0.12 to 0.16 solar emittance values, depending on what your climate zone is. They're generally the same, particularly in daytime buildings. So that's the top table that you can see here. In climate zone 5, for example, your solar emittance values is 0.13 across all 4 aspects. You can see that in climate zone 8, depending on which orientation it is, there are slightly different requirements. Okay, so, and then for overnight buildings, we can see that, again, more stringent solar emittance requirements going between 0.07 to 0.10. So with solar emittance, it's measuring how much solar energy you're letting through your construction. So the lower your solar emittance, the higher performing, or I guess the better it is in terms of that particular construction. Again, with display glazing, you've got slightly different requirements. There is a shading factor that you would need to calculate. We won't spend too much effort on it today. You can find that in the code. So let's move into our case study for compliance now. This is an incredibly simplified example. So if it's not 100% representative of what it is in real life, don't worry about it. This is just meant to demonstrate to you the concept of how you apply code compliance. So the case study that we're looking at here is a 10-story office building in Sydney. It is a curtain wall construction, and the spandrel panel component is opaque glass. On level 5, we have a plant room there. Now, the important thing to note about plant rooms when you're determining compliance is to determine if you're considering the plant room as a condition or non-condition space. So if your plant room sometimes forms the return air plenum, or if it's the mixed air plenum, you might be able to say that that is a condition space. And therefore, when you're trying to assess your wall glazing performance, you will need to include your plant room in your assessment. However, if you were to say that your plant room is non-condition and therefore doesn't form part of your building envelope, so again, building envelope has a very specific definition in the code, you want to look that up, then what that means is that you only need to assess the wall glazing construction for all the office floors, all the other areas, minus your non-condition space. So you wouldn't include any of the wall glazing construction on level 5 plant room. So the fabric details here, just a quick run through. We have a curtain wall vision glass component, which is a double glazed unit. System U value is 3.2, solar heat gain coefficient 0.28. It's 3 meters high by 1.5 meters wide. We also need to know, when you're trying to use the facade calculator, you need to know both the system U value and SHGC, as well as the glazing only. So that's the glass only minus the frame. So you can see that the glass only performance is 0.3 for solar heat gain coefficient, and then the U value is 2.0. Okay, so lower or better performing than when we incorporate the framing elements in. The spandrel glass component is also a double glazed unit. However, the frame is non-thermally broken and it's aluminium. So if you look at the different properties, materials properties, even in specification J1 point, it's one of the specifications actually, I can't remember which one it is. You can see that aluminium as a material has a very, very high thermal conductivity, even compared to another material like steel or timber. So here's an example of the detail that you might find in your drawings or your facade drawings or your section drawings. So we've got a air gap, we've got this spandrel glass, which is double glazed. So it's about 12 mils, 24 mils total, 6, 12, 6. And then we have insulation that sits behind a metal backpan, okay? And then what you can see on the right there is the slab. There is no external shading, and to simplify our example here, we're just going to assume that we have identical specifications to all orientations. So when you're looking at the facade calculator, which again you can download off the ABCB website, it's free. My suggestion to you would be to always just go and check the website before you start a new project to make sure that you're using the most recent version. So the first thing you need to do is to enter the vision glass component. So you can see that under glazing systems, I've created a glass reference, and I've just selected a G. James glazing unit with aluminium framing, put in the glass only U value and SHGC performance, and then put in the total system U value and SHGC performance. Some of these values you can often find from the manufacturer itself, or you might be able to go on the WERS, WERS website that would tell you what the U value and SHGC performances are. You just need to be careful because some of those values are quoted based on a very standard size. So if you have a custom sizing, you probably need to go back to the manufacturer and ask them specifically for your construction what the performance is. Now, the second thing that we do is then put in the wall system performance. Now, with this particular case study, we have a spandrel, which is treated as opaque wall. To make things easy, I'm just going to say that we could somehow match this configuration to the beam method in specification J1.5b, which covers, which is configuration 3, which is a thermally broken frame, okay? And the center of the spandrel panel is double glazed with a 50 mils air gap and an aluminium backpan. So we'll put in the numbers there. With the wall thickness, we need to include, so this is actually the thickness of your spandrel itself. So in this case, it was double glazed and it was about 24 mils. And then we add in the air gap, we add in the backpan thickness. So that's 150 mils. With the solar absorbance value, for spandrel units, just use the glazing or the glass SHGC value and put that in. So the next thing you need to do with your wall glazing solar emittance value is to then put in your area. Okay, so with your area, you can either put in for each glazing reference. So I've oversimplified this to say this is exactly the same across the whole building and on all aspects. But in real life, what you actually end up having is slightly different areas and slightly different windows for each aspect and maybe even for the same orientation. So you'll have multiple references on the north, east, south, and west. You can put in either the height and width of that reference, or you could calculate or measure up the entire glazing area. And then on the other side, you need to put in your opaque wall area, square meters. And that would then calculate to give you the window to wall ratio in the facade calculator. So what you can see here, they call it glazing to facade ratio. So it's 64% in this building. The other interesting thing to note on the facade calculator is I've circled on the bottom right the average wall R value that's achieved. So remember, because this building has a window to wall ratio greater than 20%, so there's more than 20% of window on the facade, we have a backstop. So regardless of everything else, we must achieve a wall, opaque wall R value of 1.0. So we've just complied here with our spandrel panels that's thermally broken at 1.09. So having put all of that values in, the calculator has told us that with our specifications that we've put in there, the wall glazing U value doesn't comply on every single aspect. So you can see that shaded there, my proposed design gives me a U value of 2.39, whereas my limit is 2.0. So I need to decrease it below the blue dotted line. With solar emittance, I similarly don't comply on every single aspect. I should be sitting at, I think this is 0.13, but I'm sitting at about 0.18. So somehow I need to reduce it. And remember, with the wall glazing performance, we can not only try to comply on every single aspect, we could try to see holistically if it complies if we apply the area weighted method to look at the whole building. And what we can see here on the right side is that the wall glazing U value of my proposed design, once it's area weighted, still doesn't comply because it's 2.39. And same issue with solar emittance, which calculates the AC energy value much higher compared to my blue box. So we're going to explore a few methods, few things that will change to try to achieve compliance. So the first thing is trying to reduce the amount of window and have more opaque wall components. Then we'll try to reduce the window U value, which means that now we have less heat transmittance through the window. And then ultimately, we'll then try to introduce external shading to try to manage or reduce our solar emittance. So here's the first thing that we did. We tried to reduce the window to wall ratio from 64% to 52%. Effectively, what we did was we reduced the vision glass height and then just increased the amount of spandrel. Sadly, while we have reduced it, the window to wall ratio by about 10%, we have improved both our U value and solar emittance values, but it still doesn't comply. So here is a report, again from the facade calculator. You can see that the wall glazing U value now has reduced to 2.09, but it's still red, so it doesn't comply. And same thing with solar emittance on each aspect is reduced to 0.14. And when we look at method 2, it still doesn't comply. So then what we tried to do with our smaller, so we're now sitting at about 52% window to wall ratio. So we then tried to change our glazing selection. We've reduced it to a lower U value. So going from 3.2, which is double glazed, but still going to another window that is now 2.8. Now the issue is that the glazing that we've selected, while we have improved U value performance, the side effect is that our solar heat gain coefficient of the window has increased very slightly. So with this change in window, we have now made our U value compliant, but because we've now increased the solar heat gain coefficient, our solar emittance requirements still doesn't comply. So you can see here, our window glazing U value is now green, solar emittance is still red. So what we then decided to do is to introduce some external shading. If you really wanted to, you could probably try to keep reducing your window to wall ratio, because now you have less window. It means that you've got, I guess, less solar admittance through the windows. But what we did here was to introduce external shading. So we introduced some sunshades. So it needs to be horizontal shading. And you can see here that, as I mentioned, there is a formula that calculates your shading coefficient that's based off how far out it projects away from your glazing itself. So that's P. It's also a function of how high your glazing component is. So that's H. And then there is another coefficient you need to know, which is G, which is the gap between the top of your projection to the top of your vision glazing. Okay, so what we did here was to introduce a projection depth of 1.35 meters for our, I think it was 1.5 meters high, 3 meters high windows. And then we'll see what happens. We've kept our glazing selection from a previous iteration. And now we can see that, again, this is taken through facade calculator. If you look at our U values, all of our facades comply. When we look at solar emittance, we can see that north and the west is now lower than the blue line, but our east and the south still doesn't comply, sadly. But because we can use method 2, which looks at the area weighted average of all facades, and also it applies different weighting factors to your north, west, east, and south, we can see that our overall AC energy value is now lower compared to DTS requirements. So overall, our building now complies. So there's a few notes here about what we just went through in terms of trying to make our building comply. One is the practicality of a projection depth. We've allowed for 1.35 meters away from the building. In reality, that might not be feasible because of structural concerns, or that might be Australian standards that don't allow that to happen. The east and west shading we've applied, we've applied some horizontal shading just for the purposes of this case study, but we know that in Australia the sun hangs quite low on the east and west aspects orientation, so it might be actually more useful to use vertical louvers instead of or bright soleils instead of using a horizontal shade external shading projection. And then the issue is that in the deemed to satisfy requirements under section J for wall glazing performance, it only looks at horizontal shading projections. So if you had anything that was vertical, or if you had some louvers or bright soleils, then you need to go through a performance solution rather than using deemed to satisfy. A key item with the 2019 changes is that buildings with very high window to wall ratios, a high level of glazing, will find it much, much harder to comply using deemed to satisfy requirements in the 2019 code. Okay, so we're going to move on to, I guess, the last part of this presentation, which was to look at a case study where we modeled a building in two cities or two climate zones, Brisbane and Melbourne, just to see what the impact of changing our building fabric performance might have on building energy, some of the peak loads, not using Camel, still using the energy software, but gives an indication, as well as thermal comfort. So looking at this here, yes, that building there was, the model that we've used has assumes basically large glazing that stretches all across the building, but we've basically just replicated a similar model that was used for the Section J revision works. So this is a 10-story office building, about 9,000 square meters in Brisbane and Melbourne. Window wall ratio is about 56%. It's a standard lightweight steel frame construction. From a HVAC perspective, we have center and perimeter zone AHUs, air handling units. It's a VAV building. We've got centralized chillers, and then our boilers are condensing boilers, but gas fired. On our windows, we have double glazed units that are filled with argon gas. So a U value of 2.71 and solar heat gain coefficient 0.21. And I've already mentioned our walls, which has 21 mils of insulation. So we just modeled a few scenarios just to see what the impact might be. Essentially, there are 4. One is we changed our window from a double glazed unit to a single glazed unit. So going from going from our U value of 2.71 to a U value of about 5.7 on our single glazed unit. Then we looked at what if we change the solar heat gain coefficient of the windows. So we've doubled our solar heat gain coefficient from 0.21 to 0.42. Essentially, that's going from a tinted double glazed unit to a clear double glazed unit. Then in the third scenario, we looked at enlarging our window to wall ratio, so going from 56% to 75%. So you can see that when we calculate the equivalent U system value is now 2.28 and the solar emittance is 0.16. They're both not compliant. With scenario 4, what we then did was to keep that window to wall ratio that we've enlarged it to, so 75%, but then try to improve the performance of our glazing so that now we have compliant solar emittance. Now, just a note here that it still doesn't comply from a U value perspective. So what were some impacts on the peak loads? We used IES, virtual environment, to do this simulation, and the peak loads are purely just looking at our model results and then seeing what the peak thermal load is on our plant is from that. So on the left, we have climate zone 2, and on the right, we have climate zone 6. So my graphics are not showing up properly, but basically look at the left first. A few things to note. On the y-axis, we're just comparing to say, when comparing the scenario to our DTS compliant case, fully compliant case, what is the percentage change? So if it's a positive change on a y-axis, then it means that, so for example, in this first one here, the peak cooling capacity of our chiller increases, okay? So a few items to observe from this. In climate zone 2, which is our Brisbane, we can see that when you reduce your U value of your glazing, so going from double glazed to single glazed unit, when you reduce your solar heat gain coefficient performance of your glazing, so going from a tinted version to a clear version, when you increase the window to wall ratio of your external wall, you can see that all of those cases will increase the capacity or the peak cooling and heating capacity that is required in the building. This is particularly bad. So you can see it's about 75% increase in peak heating capacity for the boiler in Brisbane, in this case, which is not known to have a lot of heating requirements. Okay. So the other thing we looked at here was the amount of airflow that will be required through our air handling plant. So what we've done here is to zone it out. So we've got center zone, starting from the left, going to west, north, east, and south AHUs. Forgetting about the detail in there, we can see that overall, with the what they call reduced performance or lower U value and higher solar heat gain coefficient, we can see that in most cases, the amount of airflow that's required to counter poorer building fabric performance increases. Now, there are some exceptions. So in the center zone, when you increase your U value, the center zone airflow requirement drops. Same thing with east, very slightly. Okay, and we see similar trends in climate zone 6, okay? Except for the south, where we see that with poorer solar heat gain coefficient, with the south, you actually reduce the amount of airflow that's required because now you let in more solar emittance. So impact on energy consumption. What I've done here is to just box this up to say on the left, that is the subsystem breakdown in energy consumption, and then shaded in yellow is your total building energy consumption. So again, looking at the macro trends, we can see that when we reduce all of our building fabric performance. The chiller energy increases just under 50%. Our fan energy sort of reduces, our pump energy sort of stays the same. And heat rejection fans, so we're talking about cooling towers and any condenser water pumps, also stays relatively the same. Now, the big item to notice here is, of course, in blue, that's our boiler energy increases significantly, close to 400% or 4 times compared to DTS values when we increase or convert, again, going from a double glazed window to a single glazed unit. In climate zone 6, we sort of see similar trends, but now it's sort of accentuated because climate zone 6 is much colder. Now, it will be interesting to then look at energy expenditure. And the key thing here is, if we recall, in the previous slides, we saw that heating energy increased substantially in the form of boiler energy, which uses gas. What we see though in scenario 1 is that even though we saw between 200 to 400% increase in boiler energy, our energy expenditure barely increased. Okay, this is probably a 1 to 2%. And the big key reason for that is because of the difference in cost for electricity and gas. So you can see here, I've just converted the electricity tariff to gigajoules for direct comparison. We're looking at about 4.5 times to 5 times higher cost for electricity compared to gas. Now, of course, this would look different if you were to use an electric heat pump, for example. But the rest of it, in all other cases, you can see that when we try to reduce our solar heat gain coefficient or reduce solar emittance performance, in all cases, your energy expenditure increases, both in climate zones 2 and 6. And this has big impacts when you're talking to the client in terms of whether you want to prioritize U-value performance or solar heat gain coefficient or solar emittance. The 2019 code actually places more emphasis on control of solar emittance, which is sort of aligned with what we know about climate change and a gradually warming climate. I don't spend too much time on thermal comfort. Just to note that with the DTS requirements, it was already sort of quite high in what we modeled here. We were already looking at about 97% of the time these PMV, predicted mean vote requirements, were met. And in most cases, in climate zone 6, it's going to 100% most of the time. Quite odd, I have to say. But I would like to bring your attention to climate zone 2, where we see that when we reduce our glazing performance, so going from tinted to clear, so we've increased our solar heat gain coefficient, you can see that thermal comfort actually reduces, and it's noticeable here. All right, so just to conclude the presentation today, I've gone through an overview of the Section J requirements, talked about how it's now been simplified to 4 aspects: North, East, South, and West. I've talked about how you can use 2 methods to comply, looking at it on a piecemeal basis, as well as a holistic area-weighted multiple aspect method. And I've also gone through very quickly how thermal bridging is now front and center. I've also gone through with you a case study where we used the facade calculator to help you change your design for compliance, as well as a case study looking at what the impact of changing glazing performance and window wall ratio is on energy, thermal comfort, and peak loads. So this concludes my presentation. Might move on to the Q&A now. All right, so just answering the first question. So Manfred's asked, what is the solution for thermal bridging as shown in the example with timber? All right, so if you had a timber framing system, what you would do is you use the, well, one is open up the New Zealand standard 4214. There is actually an example there that shows you how you calculate the width and the distance between studs, for example. And you would still apply the same principles in your in the facade calculator. So the only difference is that you don't need to put in things like a base metal thickness, for example, because it's not relevant. So the facade calculator does give you that flexibility to do that for timber framing. But again, download New Zealand Standard 4214. It would really help you in this process. Okay, so another question from Lawrence, who's just asked if we treat internal envelope walls just like external envelope walls in 2019. That is a good question. So if you had internal envelope walls, the code right now doesn't actually specify different requirements for external and internal walls, and therefore you'll be expected to treat it the same way because it's the building envelope. Yep. Okay. So Lawrence has asked a question about reduced thermal performance at the slab edge between the levels in the example. So a key item here is the Section J requirements, particularly those that you see as a DIM configuration, doesn't actually account for this sort of examples here. So we know that with spandrel panels, there are sort of three main configurations, and you can look that up if you like online in different material. But one is where, you know, you're just sitting in space between slabs, and then there are the more realistic versions which sit at the slab itself, or it might sit, you know, halfway through the slab, and then it might also then have insulation that sits above the slab. So the implication of that might be that the insulation sitting at the slab might be a little bit thinner compared to the insulation that sits above the slab. Now, in those cases, you can't use the DIM configuration because it is different. That is when you need to use the formula that is provided in specification J1.5b. Now, what does it actually mean in practice? It means that my suggestion to you would be to probably use a combination of window and therm. Those are the window modeling software for heat transfer. And they would then tell you what the edge related U value is compared to your center of pain and then your framing, and model it accurately for you. The other thing to note here is that with the thermal bridging provisions in the 2019 code, yes, it's done a lot by targeting framing or repeating thermal bridging through framing, but there may be other sources of thermal bridging which is not explicitly covered in the code at the moment. So for example, you might end up with a few constructions where you have your concrete slab extending all the way out. So balconies, for example, is quite common, or terraces. In those cases, it's quite complex, and the code doesn't specify from a DTS perspective how you actually deal with it. So slightly more silent. So if you want it to be really accurate, ideally we do actually model it, for example, because we know that these linear thermal bridging pathways can significantly affect your overall R value of your external wall construction up to about 70%. So I'm not saying the code has all the answers. It's certainly ideal if you considered it. And of course, the code doesn't also specifically target point thermal bridging. So if you had some nails or some fixing or fasteners, those are not explicitly addressed. They're just addressing, taking it one step at a time and starting with framing elements. The requirements for internal glazing, I'm not quite sure what you're referring to, but if it's not part of the building envelope, then it wouldn't be subject to the wall glazing requirements in the code. Yeah, okay. So in the glazing systems tab of the calculator, question from Derek, for single glazing doesn't allow a total system U value exceeding 5.8, whereas the manufacturer's WERS data indicates that the total system U value is much poorer at 6.3. Is there a reason that the facade calculator has that limit? Look, I can't tell you if there's a reason for it. I don't know why they've limited it to 5.8 specifically, particularly for non-display glazing examples. My suspicion is that they're probably thinking that it won't achieve your 2.0 anyway. But if it is a serious issue, then my suggestion is to use the race date of the ABCB so they can update their facade calculator accordingly. There are also softwares out there right now that's not, it's not a formal, I guess, ABCB release facade calculator that could help you if you're just doing it for the purposes of assessing what the impact might be. So you might want to explore those avenues instead of going through the official ones. Okay, so with the, Lawrence has actually asked a question to do with floor insulation or floor insulation requirements instead of wall glazing. I will answer it, even though it's not really part of a presentation today. So the question from Lawrence is regarding the R value of soil that's in contact with a floor. Is that applicable regardless of whether the walls are constructed on the slab or around the slab? Okay, so this is a question that was unclear in the current 2019 code, and actually the ABCB is has commissioned work. Actually, I've done some work on it, and my understanding is they'll probably either release some sort of guideline or they'll have the clarification ready for you if you ask them. But basically, again, looking at the New Zealand standard 4214, and the SIPSI method, which is another method that is referenced in the 2019 code now, the expectation is that your wall should surround or enclose your floor or your slab, essentially, because that's the one that gives you the insulating or reduces the amount of heat transfer, because the heat transfer pathway is longer to your floor. And also, yes, it's only applicable for floors that are in direct contact with soil. This is not applicable for suspended floor. Okay, so Cody, you've asked a question about using device with the facade calculator if they were to use vertical blinds. Yes, if you can prove it that it's fully motorized, for example. So let me just find to see what the exact wording there is. So with the glazing provisions, it talks about 1.5a. Okay, so it talks about an external shading device such as a shutter, blind, vertical, or horizontal building screen, which, so two things you need to make sure you can comply. So one, is it capable of restricting at least 80% of summer solar radiation? So you need to prove it somehow through modeling perhaps. And if it's adjustable, if it will operate automatically in response to the level of solar radiation. So if you can prove or model any of those, then yeah, go ahead to do that. But there is some modeling that's required, or some extra evidence that you need in order to prove that. Okay, so Nicholas has asked if we know that there are any allowances for aspect rotation in the DTS calculator. I'm not entirely sure what you're talking about here. I'm going to make the assumption that you're talking about slightly offset orientation. So instead of purely north, it's looking at northeast and northwest, southeast, southwest. The code does talk about, I think it's, they've got degrees of reference on, you know, how much to northeast will you go to classify as north, and how much you would need to go, you know, to classify it as south or east, for example. So have a look at the code there, but there's no specific allowances for you to say that it's northeast to a certain degree, for example. Okay, so Sandra, you've asked a question about thermal break calculations. So the code itself in part J 1.1, I think that's what it is. So that's what we talk about the thermal constructions. There is a requirement that you have a thermal break between any element that's in direct contact with the external cladding, and it's R0.2 if I'm not directly mistaken here. So often what buildings will do, they'll either put a thermal break, or more frequently they'll just use a thermal shaft, which is just a continuous layer, that's thin layer that sits between your cladding and your framing elements. With that, what you would do is, if you look at the New Zealand standard, is defined as, you do actually incorporate that in terms of its R value in your thermal bridging calculations. So that would be the best way that I can describe it, as yes, it is considered, but you will consider it within your NZAC as New Zealand Standard 4214 formulas and methodology. So let's see here. The peak load in Brisbane happened in winter time. It's only 10 days in a year during 3 months winter, whereas the other 9 months are cooling dominant. How does the heating energy for these 10 days justify the higher requirement of solar heat gain coefficients, say double glazing? Well, if you're going between, say, single glazing and double glazing, my comment to that is that it actually affects the U value, so the amount of heat transmitted through your glazing. So I would say that U value would be important. So if you're trying to target solar heat gain coefficient or control solar emittance, which is what I would say you generally would be in Brisbane, that's where we start to consider sort of tinting and the size of your vision glazing component, as well as the use of external shading. I don't know if this really answers your question, the person that asked the question, but feel free to send me a message or email if that didn't. Okay, so Matt, you have asked a hairy question. So Matt, you've said that you've commented that the overall impacts presented on energy consumption seems relatively modest, but in general, you've mentioned that 2019 revision provides 30% performance improvement. All right, so we're really talking about two different things here. So that 30% performance improvement came about where we modeled the 2016 DTS requirements to 2019 DTS requirements. So between 2016 to 2019, a DTS compliant building reduces their energy consumption by about 30%, roughly speaking, with that change in compliance levels. What we've presented here with the case study 2 is looking to see what the impact might be if we just change one element. So often what will happen in buildings and designs, I suppose, is we're trying to keep costs low, and the first thing that gets sacrificed is often glass performance. And often people will say, well, can I get away with just using single glaze units? Can I get away with using thinner glass or no low E coating or tinting? And that's what we're trying to present here in terms of what the impact might be. And just to give you a little bit of context when you're talking to your clients about the impacts of what they want to compromise or reduce performance might be on their building.
Great, thank you so much for that, Grace. I think that's all the questions, so well done getting through all of those. So we might wrap things up there, everybody. So thank you everyone who registered and attended today's session. And a special thanks to Grace for conducting today's presentation. Today's webinar is the last of the Streamline sessions for 2020. So to view any of the past Streamline sessions, please visit the AIRAH website, and we have a whole list of them up there for you. Be sure to also check out the Summer Skill Up for free and discounted opportunities to earn CPD. And for more information regarding the Summer Skill Up can be found on the AIRAH website as well. So thank you again, everybody, for attending, and I look forward to seeing you all again in 2021.